you'll see why it's left in a moment, times U1 Y, and the Y stands for hypercharge. Okay, so the basic idea of the standard model is that this is the gauge group. And that all of physics should be invariant under transformations, local transformations in this group. So now we have to decide what the particles are, or what the fields are, and which representations of this group the fields transform in. Okay, so this automatically gives us 12 propagating gauge bosons. Okay, why? Well, U1 has 2, right? So this has a vector potential. We're going to call the vector potential. Yeah, that's right. The Lagrangian for the vector bosons is just minus 1/4 F mu A F mu A, where A is 1 up to 8. That's the dimension of SU3. So these are the color gauge bosons. And then we have minus 1/4 F mu I F I mu. It's not very imaginative. I equals 1, 2, 3. That's the SU2, the weak bosons. And then we'll write the other ones like this, minus 1/4 B mu mu. So this is the SU3, SU2, and this is the U1, where B mu is d mu B mu minus d mu B mu. This is U1Y. Okay, so the gauge bosons just have Lagrangians, which are essentially identical apart from the group structure. And why are there 12? Well, there are 2 here, because this is a abelian group, just like electromagnetism. And in electromagnetism, you get two transverse polarizations of the photons. So we get 2 there, and then for SU2 we just have 3 different field strengths, because I goes from 1 to 2, 1, 2, 3. So we get sorry, actually I'm going to count that as one gauge boson, and 3. We get 3 for this, 8, yeah, sorry. So we actually get 24. Well, we get 12 propagating gauge bosons with 2 spin degrees of freedom each, or 2 helicities each. Okay. So 8 plus 3 plus 1. Okay, so now we've got to decide what representations the fermions are in. So the fermions are first of all the leptons. So the leptons include things like the electron, neutrino, and the electron. And they are described by their left-handed fields. So you should think of each one of these as a 2-component spinner under Lorentz transformations. And so it's a 2-component spinner. You can describe it in 4-component notation, but then it would only be the other 2 components of the 4-component spinner that are non-zero. the way the SU, this is an SU2 doublet. Okay, so the left-handed particles, fermions, transform as doublets. And the right-handed fermions, we also have E-right, which is the right-handed version of the electron, and new E-right. If there are right-handed neutrinos in nature, then there would be a right-handed partner to the left-handed neutrino, and the existence of these guys is suggested by neutrino masses, widely observed. So these have never been seen, new masses.
So is the sp2 symmetry saying like the doublet containing, for example, no E and E, at every point in space we can rotate these into each other with an sp2 transformation?
Exactly, exactly. So in the fundamental laws of physics, there's no distinction between a neutrino and an electron. Okay, they're really they're two versions of the same thing. One way of saying it is that when the Higgs field breaks the symmetry spontaneously, in whatever direction the Higgs field lies in group space, that's called an electron. And in the orthogonal direction, that's a neutrino. Okay, so spontaneous symmetry breaking is essential in telling the difference. So this one's charged, and that one is neutral. So you can tell whether a particle is charged or not is also determined by the Higgs field switching on. We'll see that in a moment. We also have the quarks. And so these, I didn't write them out explicitly. So let's call these QL, and that's a bit confusing. Let's call them capital QL. Yeah, I'll use a little q. Up, down, left. So there are two quarks in every generation of fermions, an up quark and a down type quark. Again, the left-handed versions come in doublets, and then you have upright and d-right. Okay, so with the addition of right-handed neutrinos, every particle in the standard model has both the left and right-handed version. The left-handed components are also SU2 doublets, but the right-handed components are singlets. These are SU2 singlets. They don't transform at all, and they're SU2. Push that button. So then I wrote this table. Actually, now I can discuss this table. Let's say finally we have the Higgs. So the Higgs is an SU2 doublet, and the point of the Higgs is to break that symmetry. In fact, it breaks this combined symmetry down to U1 of electromagnetism. That happens by the Higgs, and the Higgs is an SU2 doublet. I'll write it this way: H plus H0. It's a two-component complex scalar, which is an SU2 doublet. Okay, so if I rotate the two components of the Higgs field into each other, I simultaneously rotate the quarks and electrons using exactly the same SU2, 2x2 SU2 matrix. One thing I haven't mentioned, the quarks are also SU3 triplets. Okay, so the quarks have an extra index. Let's call it I, capital I. And these guys are also have an SU3 index, and these are SU3 triplets. Okay, so whereas the gauge bosons come in the adjoint representation, so there are 8 of them, the quarks come in the fundamental representation. So there are only 3 of each type of quarks, and so this I is 1, I equals 1, 2, 3, and these are usually called red, green, and blue. Not that there's any real distinction, because this SU3 symmetry is not spontaneously broken. SU3 symmetry is exact. And so you can't tell the difference between quarks of different color. So then the other thing to say is the covariance derivative. Okay, so the covariance derivative is sort of the fundamental object we use to define the theory. And basically this is equal to v mu plus I gy. So there's a gauge coupling constant for hypercharge. This number y is the generator of hypercharge transformations. Okay, so it's just a number, it's a U1 gauge symmetry, but you've got to, but every particle can have a different number here. So that the this combination is the, measures the charge of each particular particle. So that's the U1 part. And then we have an SU2 part, which is IG2, and then I've got D of W mu. These are the SU2 fields. And then I've got IG3, which is the SU3 charge. And there would be a D of whatever I call it. I don't think I've given them a name. Let's call these gauge fields G mu. The vector potentials for SU3. Okay, so whenever you act with the covariant derivative, you must decide how the field you're acting on transforms under the gauge group. If it's an SU3 triplet, like a quark, you've got to use the 3x3 matrices for SU3. If it's an SU2 doublet, you use the 2x2 generators of SU2. So for example, this would either be sigma I over 2 in the case of doublet fields, or it would be 0 if this is a singlet. You just don't have this term, singlet fields under SU2. And with the Y, you've got to use the appropriate number for Y, whatever the charge is of the field that you're acting on. Okay, so let's see how this, well, let's first of all just reproduce that table above. Now I'm going to, in constructing this table, I'm going to cheat a little bit by using this formula, okay? And I'm going to justify this formula in a moment. So what I will show you is that when the Higgs mechanism happens, there's a combination of the generators of SU2 and U1, which is unbroken by the symmetry. And that's this combination Q, and that's the generator of U1 electromagnetism. So I'm just going to assume this formula, but this actually follows from the Higgs mechanism, as I'll show you. In a moment. Okay, so, but it's an easy formula to remember. And if you just remember this, you can reconstruct the whole table very easily. Okay, that's why I like putting it up front. Okay, so let's think, given that the electric charge is T3. Now what is T3? T3 is the generator of SU2. So if I'm in SU2, in a doublet representation, T3 would be the matrix, would be a half sigma 3. So T3 is this in the doublet on a doublet. Right? And it's 0 on a singlet. Okay, so T3 is very easy to remember. The charges is quite easy to remember, what the electric charge are of any particle. There's not so many to remember. And then you can infer from this equation what the hypercharge is. So we're working backwards to figure out what are the charges under U1y that will give us the correct electric charges. So let's start with the electron neutrino, left-handed. So it comes in a doublet, mu e, and so obviously it has T3 of a half, it's the upper component. Electric charge is 0, must have a hypercharge minus a half. Okay, so this guy is in the same doublet. The SU2 commutes with the U1, so it better have the same hypercharge. And Q is T3 plus Y, and has T3 minus a half because the lower component. Add these two, you get minus 1, which is the charge of the electron. Okay, so let's keep going. Right-handed electron. It's a singlet under SU2. It's not in a doublet. T3 is 0. Electric charge is minus 1. It's the same as the left-handed electron. Must have hypercharge minus 1. Okay. Now, quarks, you have to remember the 2/3 and minus a third, which is a bit of a pain. But, you know, a proton is up, up, down. And a neutron is down, down. What is a neutron? Down, up. So, yeah, so the up quark has charge 2/3. Down quark has charge minus a third. So this is a proton, which is plus, so Q is plus 1. Down, down U is minus a third, plus 2/3, so charge is 0. Okay, so it's reasonably easy to remember what the charges are of the up and the down quark. Now, if I know its charge is 2/3, it's in a doublet, it's the upper component. What does this have to be? Well, in order to get 2/3, I need to add a sixth. Okay, so hypercharge is a sixth for the right-handed, for the left-handed up quark. Same argument here. It's the hypercharge has to be the same in the upper and the lower components. It's in the same doublet. Right-handed guy, charge is 2/3, hypercharge must be 2/3 because the T3 is 0. Down right must be. My numbers align not very well. Minus a third. Okay. Right-handed neutrino, charge is 0. T3 is 0. Can't have any hypercharge. So that's a very unusual particle. It doesn't have anything under the gauge group. Okay, and that's in fact why we believe its mass can be huge. It has a bare mass, which is huge. We predict 5 times 10 to the 8 GeV. It's much higher than anything else. Okay, so Higgs field. Well, I've sort of cheated a little bit and told you that the upper component has charge. In fact, yeah, the best way to do it is to say the component that's going to get the VEV is neutral. We don't want the vacuum to have a charged field sitting in the vacuum. So this guy has to be neutral. We're going to put the field in the lower component, and we're going to call that neutral. So H0 has charge 0, has T3 of minus a half, so it must have hypercharge of half. The upper component has to have that same hypercharge, and therefore its charge must be 1. Okay, so that's it. So if you know this table, and you know the covariance derivative, you know the Standard Model. There's nothing more to it. Now, I'm going to go through this calculation and show how this calculation comes out of the Higgs mechanism. So how do we do this? Well, remember the origin of masses in the gauge theory is just this term. And I'm going to cheat a little bit by ignoring all the fluctuations around the point on the vacuum. Okay, they're sort of obvious, right? So in this case, we've got a vacuum which is h dagger h is v squared over 2. The h is a complex doublet. So this describes a three-dimensional sphere, right? The you can write h is, let's say, h1 plus I h2 in real fields, h3 plus I h4. And so h dagger h is just the sum of the squares of these guys. That's a three-dimensional sphere. So the vacuum of the Higgs potential, the minimum of the Higgs potential, is a three-dimensional sphere. And the SU2 moves you around on that sphere. It's not hard to show that any point can be moved to any other point using SU2. So I'm going to cheat a little bit by just picking some point on that vacuum. Let's pick this point, 1 over root 2 v. And I'm going to ignore the fluctuations. There are two kinds of fluctuations. One is radial, and those are massive particles. And then there's the angular fluctuations, and the angular ones are going to get eaten by the vector bosons. Okay, so let's just not worry about them. Okay, that will all get taken care of itself. So now we're going to work out what is this. What is this equal to in the vacuum? So let's just work out, let's call this H naught. It's the constant Higgs field in the vacuum. So d mu of H naught, well, the ordinary derivative gives 0. So it's just the vector, it's just all these other terms. Okay, so I just have to work out what that is. That's equal to, so let's write it as a 2 by 2 matrix. It's I over 2. So I'm just taking that formula there. Hypercharge of the Higgs field is half. So I've got gy over 2. So we have gy b mu, sorry, a bit bigger. Gy b mu, that was the U1 gauge field. And that comes into both components, because it's both components of the doublet have the same hypercharge of a half. So I get this, the 1/2 comes out the front. And now I have to work out how the SU2 acts on the Higgs doublet. So that gives me plus it's plus G2, the I is out the front, plus G2 W mu, I'm going to make it a bit bigger. Where is the, need more space. Okay, so I over 2, gy b mu plus g2 w mu 3. Down here I've got gy b mu minus g2 w mu 3. Okay, so all I use to get this formula is the fact that the T3 generator of SU2 in the doublet representation is a half sigma 3. So I've got the half, and then sigma 3 is plus 1 here and minus 1 here. Now let's do the off diagonal ones, and I get G2 W mu 1 minus I W mu 2. Why? Because W1 comes with sigma 1 over 2, and W2 comes with sigma 2 over 2. Sigma 2 has this minus I up here, and then I have the Hermitian conjugate down here. So W mu 1 plus I W mu 2. Okay, so that it's that matrix acting on 0 and V over root 2. And so now all we do is work out d mu h0 dagger d mu h0. And we could read off all the quadratic terms in the vector bosons. Okay, so how do I work this out? Well, I multiply this matrix by that column, and so this term gives me I over 2. This times that gives me, well, let's bring it out in front. V over root 2. And then I have G2 W1 mu minus I W2 mu. And then this multiplied by that gives me Gy B mu minus G2 W mu 3. So now I calculate the mod squared of that complex vector, and I get V squared over 8 from this factor, and then I get G2 squared W mu 1 squared plus W mu 2 squared. And then I get plus G2 W mu 3 minus Gy B mu all squared. It's just this term squared. Okay, now these terms are quite easy to interpret because these are literally mass terms, just like we calculated before when we did the abelian Higgs model. These are mass terms for the W bosons. And taking into account the factor of a half, the minus sign, because it's only the spatial components which are propagating particles, we see that the mass here is G2V over 2. Okay, and this is the W boson mass. Masses after symmetry breaking, spontaneous symmetry breaking. So they depend directly on this number V, the Latin expectation value of the Higgs field. Okay, so these ones are easy to interpret. This one's a little trickier because the linear combination of the U1 vector boson and the T3 vector boson coming from the SU2. And it's this combination which gets a mass. The orthogonal combination that is massless, and the orthogonal combination is the photon, right? Which remains massless. So how do you deal with this? So notice that the kinetic terms for the gauge bosons, which we wrote down up there, are minus 1/2. Right, so they include terms, minus 1/2 d0 bi, sorry, plus 1/2 d0 bi squared for the U1 gauge bosons. Yeah, if you think about the indices, raising and lowering, just remember that whenever there's an I, you get a minus sign. You get, instead of a quarter, you get a half, because there's F0I and Fi0. So you get the right looking kinetic terms for the spatial components of the vector bosons. And they're properly normalized as a real propagating field, right? This is compared to the scalar field, which would be a half d0 phi. Similarly, for the W mu 3, I get 1/2 d0 Wi3 squared. Okay, reading off from the SU2 part of the Lagrangian. Notice that this combination is invariant under rotating B and W3 into each other. It's a sum of squares, right? So I can, this is invariant, so the kinetic terms are invariant, the sum of the kinetic terms is invariant under rotations. These are W mu 3 goes to cosine theta W mu 3 minus sine theta B mu, and B mu goes to, yeah, let's call this, let's call that W prime 3, and B prime mu is cosine theta B mu plus sine theta W mu 3. Okay, so this kinetic term is invariant under rotating the B and the W into each other. What you want to do is do such a rotation such that this massive field is separated from the massless field. So what do? We want to choose this equal, we want to choose this to be proportional. We want to choose theta so that this will indeed be the W3 prime, which actually I call Z mu. Okay, so define Z mu to be a rotated version of W mu 3 and B mu, which is proportional to exactly this. So what do? We say Z mu is equal to G2 W mu 3 minus GY B mu. Okay, that's good, but these are not angles. So I've got to divide this 1 over square root G2 squared plus GY squared, so that this is a cosine and that's a sine. You want the sum of squares of these coefficients to equal 1. Then this is a rotation. Okay, so that tells you that it tells you cosine theta. Let me see, how should I write it? Yeah, no, that's fine. So that tells you that cosine theta is equal to G2 over square root G2 squared plus GY squared. This is called the Weinberg angle. Okay, and basically Steven Weinberg got the Nobel Prize for figuring out that you needed to rotate this in the right way to diagonalize. What you want to do is diagonalize the Lagrangian. It's not diagonal in this form, but if you do a rotation of the field, it's diagonal. It's pretty easy to get Nobel Prize in those days. I'm just kidding. The orthogonal combination, orthogonal linear combination of B mu and W mu 3 combination is A mu, which is yeah, when I do this rotation on the orthogonal linear combination means that it's orthogonal in this sense, and it's just 1 over G2 squared plus GY squared. And so here I want to use, wherever I use cosine theta here and minus sine theta, I'm going to just do the opposite. So this will be cosine theta W. Oh, actually, well, let me write it out. So this will be, G2B mu plus GY W mu 3. And so this combination remains gets no mass. Okay, because only one linear combination got a mass, this did not get a mass, but this combination has the right kinetic term. So from this we can predict the mass of the Z boson, and the photon remains massless. So we see that the mass of the Z boson is so just looking up at that formula here, you can see that this linear combination is equal to the square root times Z. Plug it in there, and I'm going to get, so the Lagrangian contains this term, v squared over 8, this guy, g1 squared plus g2 squared, and then z squared. And so we can just read off that mz is equal to square root I shouldn't call it g1, gy squared plus g2 squared v over 2. Okay, so the Z boson gets a mass. It's slightly different than the W boson masses. W1 and W2 got a mass GV over 2, G2V over 2. The Z boson has the sector term here. And this is verified by experiment. And then finally, the photon. Right. So now we want to get this formula Q is T3 plus Y. How do we get that? Well, as always, we just start from the covariant derivative. Plus IG2 TIWI mu. This is the SU2 covariant derivative. This is equal to, so, sorry, and I need the G1 as well, plus I Gy Y B mu. Okay, so that was my covariant derivative on any field. I'm going to ignore color because the whole Higgs mechanism is color singlet. SU3 singlet. So what's this equal to? Well, let's focus on the T3 part of it. So it includes, well, let's see. Yeah, it's equal to that. Yeah, let's say it's equal to this. We know that W1 and W2 became massive. We know that W3, some linear combination of W3 and B became massive. Let's set the massive fields to 0. Okay, they cost energy. So let's set W mu 1, W mu 2, and Z mu to 0 because they're massive. Okay, if you set Z mu to 0, that means W mu 3 is Gy over G2 times B mu. And so then you say that you see that this is equal to B mu plus I G2 W mu 3 is Gy over G2 times B mu. Just think. just write it down and then I'll justify it. Sine theta T3 A mu. That is coming from W mu. Yeah. Ah, right. I'll write it down and then I'll throw it. Sine theta T3 A mu plus I G Y cos theta A mu. No, too many I's and things. There. Okay, so how did I get that? I look at these formulae. These formulae allow me to express W mu 3 and B mu in terms of Z and A mu. Right? So basically these formulas read that Z, let's forget about the mu index. So Z is cosine theta W minus sine theta B. A is cosine theta B plus sine W. We can invert this to say that W is, right, this is an orthogonal rotation, C minus S, SC. We can invert it. The inverse is CS minus SC. We can invert it to say that W is CZ plus SA, and B is minus C Z. No, I got that wrong. B is minus S Z plus C A. Right? And just applying this matrix to Z A. So that's the inverse. We're going to ignore the massive fields. Z is massive. So W is SA and B is CA. So that's all I did here. I took W3 as SA and B is cosine theta A. Okay, so now we've got our result because we'll see that, yes. So now I can use the formula for cosine and sine. Cosine theta was G2 over the square root of the sum. Sine theta is Gy over the square root of the sum. In fact, this is the usual definition of the Weinberg angle, because if I tell you sine theta, if I tell you that this side is positive, then the theta is naturally positive. If I define cosine theta, it's a little bit ambiguous. So this is usually the definition of the Weinberg angle, this one. But what you notice is that both of these coefficients are the same. So this is actually equal to B mu plus, now let's see, yes, that's right. We've got the T3, good. This should have come with a Y. I left out the Y. Right, so I think it's up here. And so what we've got is I G2 Gy over square root G2 squared plus Gy squared. Both of them are the same. Multiplied by T3 plus Y times mu. Okay, that tells you that Q is T3 plus Y. It also tells you that the charge of the electron, the unit of charge in electromagnetism, is E. This is the gauge coupling in E and M. Okay, so we have that E is G2, G1, and go square root G2 squared plus Gy squared. Actually, it's quite ironic because this is equal to sine theta. This is equal to sine theta times G2. This is less than 1. Okay, so the electric charge in QED is smaller than the weak gauge coupling in the weak theory. So actually the weak theory isn't so weak. Okay. The coupling in the weak theory is bigger than the coupling in E and M. In fact, E and M is the weakest gauge coupling in the standard model. And so we see from this that so now I've derived this formula T2 plus Y. Yeah.
Is this derivation universal? When we send the massive particles to zero, we
Yes.
have to do that?
It's just simpler. Okay, so when we derive the interacting Lagrangian in the full theory, we go through this awful process of finding the vacuum, considering the most general fluctuation, expand the Lagrangian in all the fluctuations you'll find. There are no linear terms because it is a classical solution you're expanding about. So no linear terms. There are quadratic terms that tell you the masses. There are cubic terms telling you the interactions. If I just force the Higgs field to be in the vacuum and ignore the Goldstone mode and the radial mode, I'm going to get this all right, the quadratic terms in the gauge boson masses. I won't see any of the interactions. Okay, but getting the interactions is just boring. It's just lots of Taylor expansions around the minimum. So there's nothing conceptual there at all. Was that the question?
Well, my question was more like, is this a universal derivation since we just ignored the massive,
yes, it is. It is because I haven't. Well, what I actually did is so I ignored the massive mode in the Higgs field. That was the radial mode.
Yeah.
Right. So forget about that mode. What I've done is explicitly calculated the masses of all the vector bosons. And what I discovered is that, so in SU2 cross U1 there were 4. There were the 3 SU2 gauge bosons and the 1 for U1, Y. And what we find is that there are 3 mass terms for the 4 bosons. So one of them is massless. So then I looked at the mass terms and I said, which linear combination is massive? And the orthogonal linear combination is massless. And then all this algebra was just to figure out which combination remained massless. Okay, there's a sort of group theoretic way of seeing the same thing, which is if you've got SU2 times U1, the SU2 are matrices like this. Your Higgs field is proportional to this. You have to think what linear combination. So yeah, so the SU2 acts on the Higgs field as T3, which is a half sigma 3. And then the U1 acts with a hypercharge. So the generator hypercharge is exactly this number for the Higgs field, which is a half. Right, so you want to say this plus 1/2. What does that look like? Well, it's this matrix here. Okay, let me just think. Yeah, so we have 1, 0, 0, 0. This is the linear combination of generators, which leaves the vacuum invariant. Right, so T3, so if you want to just think about the group theory of it, the unbroken symmetry, U1 electromagnetism, is generated by the generator of SU2 cross U1, which leaves the Higgs field invariant. Okay, so if you just want to understand which groups are unbroken, it's clear there is a U1 which is unbroken, which is the U1 generated by T3 plus Y. Why? Because the only thing that breaks the symmetry is the Higgs wave, this number, and this number is invariant under this combination. So group theoretically, this is the generator of the unbroken gauge symmetry. What you don't get from that argument is the strength of the coupling. Okay, and so you have to go through this rigmarole of finding the right linear combination in order to read off what is the gauge coupling of the U1 that remains. Okay. Now it's a funny thing because this is called a unified theory. They won a Nobel Prize for it being a unified theory, but it's not really unified because you have two couplings. You have weak force and the electromagnetic force each have a coupling. In this theory, there are two couplings at the start, so you just dial those two parameters to fit two numbers. It's not really unified. It's not unified in the sense of predicting those numbers at all. Those numbers are just dialed to fit the experiment. In grand unified theories, you are supposed to start with a single simple group with only one coupling, and the idea is to predict all three couplings, so G3, G2, and G1, starting from one adjustable parameter. So there should be two predictions, but that never really worked. Okay, came close, but was associated with all kinds of other nasty effects, like proton decay and so on, magnetic monopoles, all kinds of other things that were never seen. Okay, are there any further questions about anything actually? Yeah.
About the covariant derivative,
Yes.
how can we combine SU2 and SU3 as a matrix?
As matrices?
Yeah.
They just live in different spaces. Okay, so when you think of how this acts, this guy only cares about up, down, left. It acts in that two, so think of the matrix operating on this two-component object.